the paths and transitive closure, if I remember correctly. With transitive closure clear, because I didn't have my nicely scribbled notes with me, so I had to go off of the computer notes. Today we're just going to talk about network flows. Has anybody encountered these before? Have you seen? It's a pretty they're pretty fun. I mean, I find the textbook is really good too. I've read textbooks on algorithms before, and this one is really accessible, so I'd recommend. And I follow it pretty closely. So the general problem is you might have, a directed graph of the kind we've been considering, and it might just look like where these edges all have weights. And so the general idea is given that these all have some sort of capacities, like if we imagine this is a water system, and these are maybe the nodes where things start, and these are the nodes that will definitely give in some sort of flow of information or water or whatever. The idea is how do we approach maximizing or minimizing the flow. So this is generally speaking what we're going to consider when we talk about network flows. It's a really intuitive, dynamic programming can be a bit weird at first, but then once we get to this point, I find that this stuff's really intuitive. It's kind of fun. We're going to consider things like networks. And broadly speaking, and we'll always talk about these networks as directed graphs. Yeah, they're usually, sometimes they're acyclic, sometimes not. Sometimes they don't have cycles. There are, in these networks, there are sources. So there's two ways these networks are talked about. I've noticed that in the textbook they kind of talk about them with one source. It's useful to set up the general case though, which is that there are many sources as a big set S. Yeah, there are all the S's in V such that only edges leave. And then you also have your destinations or terminal nodes. Whoa, what did I put here? Let's call these, just call them S stars, even though commonly they're called T. So given this graph up here, these guys would be in the S edges, and these guys would be in the T edges. And it's in network flows, it's usually trivial and advantageous to set up some sort of master S. That's usually just called S, and it's usually advantageous to set up some sort of master terminal node. It just helps with analytics. But in general, when you're considering networks, that's not always the case. It's just nice to know that the general case where you have many sources and destinations, you can easily just map to. and the outset. So there's this cool problem we're going to work through. We're going to draw this one diagram a lot of times today. So yeah, the core problem is to assign flow. Which we haven't really worked out what flow is yet, because we have like almost no notation. But yeah. So, I'm probably going to leave this specific guy up all lecture. I'll try not to destroy it. So this is start. This is not a 5, it's an S. So looking at this note, I've assigned some numbers, just to jump back here. So the numbers we're talking about in this diagram, labeled, for some reason that looks weird. So each edge, CE, has a labeled capacity. You know, we're also going to talk about the edges as UV pairs, typically. So, and it's just the latent capacity in the network to take flow. So given some start and end, that's that. Label has 2 L's, right? 1 L, 2 L's? I don't know. For some reason, as soon as I start writing on a blackboard, suddenly everything looks strange. Yeah. Anyway, so in this example, that's our V, and our edges are shown. So in our definition of networks broadly, we can also note that we're going to have some capacities. So we have sources, we have, let's say, destinations. And then we have capacities. C, let's say U, V. And typically they're just real numbers. Usually they're positive. And I'm trying to see if we have any specific, there's no restrictions given here, so I'll just leave it as something we'll talk about. Yeah, still wrong. Is it labeled, is it 2 L's or 1 L? Does everyone tell me?
It's 2 L's.
It's 2 L's, yeah, okay, thank you. It does look weird, it is weird, it's broken. Okay, great.
Oh no, now it's weird.
I don't understand, it's the chalkboard magic. If you guys ever write on a chalkboard, you'll know, you'll remember when it happens. So that's the general setup. And so the idea is, does anybody have any ideas of how we might go about talking about what flow is? Does anybody want to give me an idea of how to even specify flow? What is flow? What does that even mean? So you can give me an offhand definition if you want.
Max or minimize cost from S to T.
Yeah, someone's been reading the textbook. Yeah, no, it's basically that's a good definition. Yeah, we basically just want to find, you know, if we want to look at traversal paths, which are somewhat complex, and we want to say, well, if we take the sum of the steps of the path between S and T? Is there a way that we can maximize some integer? You know, if we think of pipes, the easiest example to think of is water pipes. Yeah, so, yeah, what is flow? Well, we're going to define it as a function. And broadly speaking, given some edge, so given an edge, our flow is just going to be, we'll just say it's a real number, such that it's not zero. Oh, it can be zero, but it's not below zero. And that it's less than the capacity. So it's bounded by the capacity. So it's just, we have this one constraint. Just we're gonna, so it's some arbitrary function that we want to discover. We want to find out like what this number is, and we can assign it how we like. So you said, you know, min or max. Well, the minimum is going to be 0. You know, because we can just have 0 flow through all the nodes. But what we'd like to do is assign the best value to the flow, such that we can push the most material through the network. These problems are interesting because, given everything we've thought about so far, we don't really have the analytical tools to solve this directly. Even with this introductory concept as well, given the idea that, you know, we're trying to just this one constraint that, you know, we can't violate the capacity, we have some interesting consequences. So one of the interesting consequences, knowing this, it turns out that that we'd like to, you know, if you think about pushing flow through all the pipes, like, I guess maybe I could rephrase this. Is this enough? Like, is this one condition enough? Like, can I just assign, you know, 16 and 4 here? Is that okay to do to A? Given everything we know about the structure of this network. So, just so you guys end up with it in your notes, you know, just think about this. From the start, and then this is 4. Does this make sense? Does this situation make sense? If we assign the flow values like that? Doesn't make sense, right? Doesn't make sense because so maybe the condition isn't quite enough. Doesn't work. So just through quickly inspecting the problem, we can see that, you know, 16 plus 4 is greater than 12. So we need to conserve. We need to have like another constraint on F, other than the fact that it's just less than the capacities everywhere. But we also need a second constraint, right? So this is, you know, loosely. We also need to start to consider the idea that we need to conserve flow in and out of these junctions. So.
A's capacity as well.
It's not A's capacity, it's the capacity from A to C, right?
Okay.
So we have A, C, right? And so we've exceeded that capacity, which we know we can't do, so it's not a viable solution. Not a realistic solution. Sometimes, you know, in life you might expect magic to happen. You know, maybe you pile a lot of work on your desk and you expect the flow of your homework doing at night to be really good just before the exam, but it turns out that you have exceeded your maximum flow. Really bad. It's like a dad joke, but yeah. But that's the thing. So we have to put this in analytics. So we just want to define, you know, not only the concept of the flow over or through an edge or the flow here and there. We almost like want to define the flow through a vertex, and we want to constrain that. So we can actually just define the flow in and flow out. And it's actually pretty natural, and it's what you would expect. So given a vertex, does anybody have any guesses of what the flow in will be as I'm writing it?
The sum of all U's.
Yeah. So it's just going to be the sum, make this nice and big. The sum of all the flows given over all the u's, 2v of f. They don't really specify, I mean, we could set up like it's a member of a proper set, but I think you guys know that this is just all the u's entering. Like that can be all the u's in the set of vertices even. Yeah. And this will be precisely the opposite. Oh, does that happen either? So this is a big V, obviously. All right, so this is just in and out. Yeah, and so the big assertion is that this is a quantity that's always conserved. So the idea is that we want to assert this idea that the flow in always has to match the flow out. So and so when we're considering optimal solutions for flow networks, that's the other sort of major condition that we want to satisfy. And so we might try to minimize or to maximize the flow in that network. And yeah, and this condition only holds for, I'll just write this down. It's only true for the elements that are not, you know, in the union of our, if we take our big S, so if we take our terminal node, we'll call it S star. So we're just saying for anything that's not the start or the terminal node, like for anything that's not the beginning, like we have no flow conservation here or here. Yeah. Does that make sense so far? So for our source, usually one source, so usually this will just be S and T. Other than S and T, our flow is conserved and it can't exceed the capacity. And other than that, I think we're pretty much free to have fun. So we can try to design a network that maximizes the flow. And, you know, and an initial guess, which we might construct, looks something like this. Yeah, we're going to reuse this a lot, but I just don't want to destroy the example, because it's useful to have it there.
What is your statement below formulas now? Like, what is the for all signs?
Sorry. Yeah. I'm like, might actually be the worst professor ever. I'm glad you guys think that's funny. All right. So, does that make sense though? So this is like a candidate. This is like a potential like maximizer. Is this the maximum solution, you guys think? I think the issue with flow networks is that it's really easy to just willy-nilly go through and assign some numbers, but it's very difficult to know when it's the optimum. I mean, it looks good. I constructed this, so we have a sum of 14 here. There's some interesting properties we might notice. Here we go, shit. Does that even work? That looks great. Yeah, so I mean, it looks decent. The question is it optimal? Do you guys have any ideas of how we might figure out whether or not it's optimal? Yeah, sure.
Well, like over at the very end, like if you had, yeah, so you had above it's 10 and below it's 4. Right, but like that 10 can be, that 10 value can be bigger. Because
It could be bigger, yeah, exactly. So you have 20 over there, so it's, well, we're missing out on 10 here. So we're missing, so is there an obvious way, you know, like looking at the network? Because this is already at 12, so we can't get more through there. This is giving back to, so we kind of immediately, we're like, okay, well, we want more. Like, we definitely want more. But then we have this issue, well, this is -2. We can't get more through there. We may be through here, so maybe we could try to draw more than 7. So, okay, so you can kind of like, right away you can kind of see this idea like, okay, well maybe if we go through here, you know, we have a 4 here. Okay, so it turns out that, you know, there's this path that we can sort of see right off the bat, where if we can add a number to this path, and we can potentially improve the solution. Like straight away. So it turns out that this isn't the maximum solution, and by inspection we can see that there might be a better solution. Yeah. So we're going to think about that, about given our current solution, is there a way that we can find a flow through a network or sort of a subset of vertices such that flow can be maximized? And that's actually like a general sort of, that's going to be the general approach with flow networks, and we're going to flesh that out in a lot more detail.
So that's human that backwards going arrow release and -2.
No, there's no, it's a positive.
Then the flow out for that one is 4 when you got 6 and the 2 comes into it.
Hold on.
Oh, okay.
Is it, we're okay? Yeah, we're good? Okay, sweet. Okay, so let's define total flow. So just to keep things sorted and keep things straight, let's define total flow. It's an important concept, and it's the quantity that we're going to want to maximize. So our total flow is going to be equal that doesn't seem like it makes any sense at all. And oh no, that makes no sense. Okay, yeah. So it's the total flow is going to be equivalent to the amount of like given you have a solution to the problem, it's going to be the amount that comes out of the source node, and or the amount that flows into your terminal node, right? Given other sort of spot checks, you might not be able to arbitrarily construct the same number, but that definitely holds. So you know, this is 14, and if you look at this junction here, that's 14. So that's like a kind of a preserved quantity. But as you start to look between different nodes, and isolate different nodes, you don't necessarily have that property anymore globally. But we know that like conceptually that's probably true, and it's something to think about. Like, can we prove? And we're not really going to do it in lecture, but it's just an interesting sort of hovering question that we could think about. But this contemplation of when certain subsets of the graph are, yeah.
Did you read S and T?
I did I write S and T?
S and S. Like, can we prove?
Well, S and S is a little trivial because it's one node, so that will definitely be true. But this is kind of our assertion that, you know, the maximum flow of the graph, how much throughput the graph has, given all the constraints that we've laid out. We're saying in that environment that the amount that's flowing out of the beginning node and the amount that's flowing into the terminal node will be, oh, you mean S and S there? Yes, in fact I do. I'm glad you guys are having a good time today. Yeah. So, in terms of finding solutions, I've never once pretended to be a perfect man. Did anyone get caught in the rain today? I got caught in the rain today. It was actually terrible. I had to resort to putting on another shirt and using one of the hand dryers in the washroom. It's great. Good stuff. If you're ever in that situation, it turns out it works out really well. So. Yeah, so in terms of finding solutions, we generally speaking are going to consider these graphs, just to reiterate. And when we're thinking about these graphs, can you guys think of a way, given these nodes and edges, so given So is there like a really clear, really easy optimization strategy that will get us to the best sort of to this F, if we want to say, this best version of the function of F, so we want to maximize this number. Is there an easy way to do that? That's kind of the question we're dealing with. I don't want to kill that. So, can you guys think of any approaches?
Could you maybe start by bounding, putting a bound on the F values on every single vertex?
So you're saying that you start with some sort of low flow and you build up to something else?
I guess, well, I mean, for example, at the very end T, at most it could be 24. So
okay.
Then the start node can, therefore at most be 24 as well.
Yeah, so what you're actually expressing, so you've had the intuition to express an idea we'll get to later, which is really good. And the idea is that, if you can find the network, he's saying, look at the terminal node, and it's 14, so we can't do better than 14. It's obvious. We can't, even if the capacities, if we augmented this problem and put, capacities of 100, it doesn't matter. We're never going to be able to do better than 2024. And so that's a really good intuition. But it doesn't really get us any closer to the optimal directly. I mean, if we're actually considering the nodes and vertices, we could try to consider, of course we could consider brute force. And I'm just gonna write down brute force here. Because we always have to talk about brute force. And it won't work. You know, it's something like if we consider that we're doing a set of numbers for the capacity, so we consider they're not real numbers, it's something like omega, you know, the product of all the edges. It's just huge. Like there's no way you could compute all those numbers. It's massive. So even for small networks, so that's not really a smart approach. So any of our combinational tools that we've used so far, such as like our you know, even our dynamic programming approaches to a certain extent where we consider combinations of things, those sort of ideas won't necessarily work. But we might, you know, if you think about some sort of approaches, you know, like the matrix chain multiplication, we consider iterating through k's, so maybe that'll get us closer, or you know, maybe something like that. We consider greedy approaches. And our greedy approaches, so if we consider just isolating a node and optimizing the flow of the node, do you think that would, like, if we just did that at every node, would that work? What do you guys think? If we just took a node out of the graph and said, let me try to optimize this flow at this node as much as I can. So let's consider the paths in and out. Will that work? It might actually work for some graphs, like maybe really trivial graphs, but it turns out that like these networks in general, they don't necessarily have the property that the locally optimal choice for the node is the best choice for the graph. It actually turns out that sometimes some nodes not fulfilling all their capacities is optimal for finding solutions later on. So local capacities. Basically, we have no greedy choice property. And then really, when we consider, well, we don't have a greedy choice property, do we have optimal subproblems? So we consider, again, considering these nodes and edges, is there a way we can break sets of nodes or edges down such that we can consider a dynamic programming approach? And you guys can try it. It's very hard on a vertex restriction basis. If we consider what we learned last time with taking, you know, like one vertex out, another vertex out, and considering subgraphs. Sometimes when you add another node, it just completely changes things a lot. It can be very, very difficult for some graphs. To specify recursive like optimal subproblems. So that's like all our tools, and I guess we're done. So that's it, right? Turns out that there are. It turns out that the major problem or the major assumption we're making here, the major sort of sub-problem that we're focusing on is not the best one. Does anyone know what we might be able to consider instead of considering vertices in isolation? And you already said it, basically. I just wanted to make you guys think about it for a while. You have to consider all the vertices at once. And it turns out if you consider all the vertices at once that it is possible to consider augmenting the graph. And it is possible to consider these optimizations, these piecewise optimizations you can make to your graph And that is, it turns out that's the fundamental idea behind the Ford algorithm. And I wouldn't naturally, if I was sitting on the couch, have this intuition, but it's, thanks to the guys who wrote the textbooks, like a lot of smart people have thought about this already. And thankfully, it's a pretty cool idea. And so it turns out that if you can specify a problem as a flow network in some way, then you can apply an algorithm like this to solve it. And so this kind of will end up in your tool set. So let's consider let's consider the general idea first. Of improving the network. So, the first thing we might be able to do is establish some sort of minimum flow. So, given these guys, we might define some app. I was going to use a an index sometimes, say like a time index. So this is like, if we imagine we're at index 0, we might assign this sort of thing. Maybe these are the only ones that have values at this point. Everything else has no values. So we might just start there. And then we might consider, some really crunched up version of the existing diagram at F2. And this is the general paradigm of the Ford algorithm. The idea is that in this transition, we make, and this is where I find that it is really kind of a greedy algorithm. It's not talked about as such, but we do make greedy improvements. I'll just write greedy changes to the, I still ran out of space, network. So the key point here is that instead of viewing the problem that we're dealing with as one vertex at a time, we're considering the subject that we're improving to be the entire network. And that's really what characterizes, if you notice what characterizes improving network flow versus every other problem we've dealt with so far, is this idea that we're taking the network itself and making improvements to it versus restricting subparts of the network and improving those specifically. So in every iteration of this algorithm, what we end up with after a full execution is the whole network that is slightly transformed from our analyzing it. Does that sort of make sense that we're talking about the entire network and not just a single vertex?
For your improvements, why do you neglect the interior edges?
I didn't change them. I'm just assuming them 0, so I just didn't draw them, but I can draw them on as zeros.
But why aren't they 1 like every other edge?
It's just a potential first, it's very arbitrary. So we're just saying this is something we might do. Whether or not an algorithm would actually make that specific improvement, probably not. Yeah, just the initial investigation. Okay, just for illustration. Yeah, no good reason. Definitely no good reason. This is not like anything other than for thought. Yeah, so there is a massive general assumption that the Ford algorithm makes. Can we write the name of the algorithm yet? No. Okay, so let's write that right here. Oh, okay, it comes up. So the general assumption is that incidental or incremental changes so if we say we have some ft and it's, being assigned to by some, or some, f, and it's getting assigned ft plus 1. So we have this, this time index, we're slowly, I kind of jumped 2 time indexes, but this can be 1. This is just for illustration. But the idea is that over time, the effective flow that we're considering changes. That eventually f will equal some f star, such that it's worth noting that, in these networks, it's possible to have multiple optimal solutions, but we just want to make sure we find one optimal solution. And this job, this idea of, we keep updating our current flow with some sort of candidate flow we find. So we're like, oh, we could do this next iteration of the algorithm. Let's assign that to our current f. And we keep doing that. The idea is that if we keep doing that, we keep augmenting our network, given everything that we know, that we will settle on some f star. Yeah. So the question is, will that work? And I'm going to introduce you to the algorithm now. Forward focusing algorithm. Yeah, so the general idea is to find flow paths. So given what we've just considered, we might actually have a couple interesting flow paths to consider. We can have, I'll just write a couple out. And this can be at time 0. And we might generate a map of the capacities. With S, A, C, T. And this might be, path 1. We might have some path J, and it could be perhaps the bottom one, say. And there's many combinations of paths to consider, but there's a lot less combinations of paths than there are combinations of all capacities and all vertices. So that's a good sign. So this can be, this idea makes sense of isolating paths out of the network. And so we can consider these paths in isolation and see if there's anything we could do, if they're missing any capacity. So at the outset, these different paths, can anyone spot check tell me about the potential of this first path, given that we have no flow? Given that, currently that, that the total flow for time index 0 is 0. What's the flow that we can put through path 1?
12.
Yeah, it's 12. So, P1, the flow, if we want to, I haven't defined it yet, but if we want to define flow for a path for P1 can equal 12. And if we want to define flow for Pj, it's just equal to 4. So in this case, this might be preferable, maybe. Depends on the algorithm. Yeah, and so the general idea of the forward focusing algorithm in this case is the intuition is that if we have some So if we have a flow through a node, say PJ, increased flow. So the general idea is that, you know, we might already have assigned flow through some of these vertices. They might already have some real numbered flow, they might already have FE values. You know, it's possible that, I'm just going to put the flow values above. We might have, you know, already have this happening, right? So given we already have this flow, then, you know, the maximum capacity we have to increase flow is actually only 2, because we're already pushing 10 through this pathway. So, but we could improve by 2 more. We also, it's important to note that, you know, there are paths that lead through from other directions. So it's completely possible that when we analyze a subpath, that we might see something like 5, and then we already have a 10 for the flow of this edge, and then we have a 10 here. That's possible. So it's not always that these paths have the same flow through them in their entirety. Does that make sense? These paths, because of the relationships between the nodes, you can have a higher number here than here for your current flow. And we haven't really formalized this concept yet that flow can be higher or lower. And so when we're talking about networks, so far we've focused on completely on talking about capacity, and we've thought of flow as this abstract concept. But at this point, it's useful to start really formalizing this conversation about, given a path or given a bunch of edges, how do we capture the current status of flow? And that's actually in this method and in this algorithm, that's where we get into this idea of something called residual capacity. It's basically the residual, the unused capacity in an edge. And it's a way to formalize and talk about that with strong language. What time is it? Is it 7 on the dot? Oh. Should we take a break? Wow. All right, let's take a break. I think I'm getting a spidey sense for this stuff.